In this video, we're going to investigate one of the most interesting images in mathematics, the Mandelbrot set. Now, as many people are aware, the Mandelbrot set is one of the most beautiful objects in all of mathematics. But what most people don't realize is that the mathematics behind the Mandelbrot set is equally beautiful and equally interesting. So in this video, we're going to look at some of the elementary fractal geometry and number theory that lurks behind the Mandelbrot set. Now, the Mandelbrot set was first discovered in 1980, so all of the mathematics that we're going to talk about is mathematics that's been done in the last few years. You might wonder how you will understand this modern mathematics. Well, it turns out that the mathematics behind the Mandelbrot set is incredibly accessible. In fact, by the end of the hour, I'd like to finish up by showing you how to use the Mandelbrot set to count. And then towards the very end of the hour, we'll get very advanced and I'll show you how to add. So the mathematics here should be quite accessible. Well, let me begin with a brief tour of the Mandelbrot set. Here is the Mandelbrot set in black. You see there are lots of decorations on the Mandelbrot set. Let me zoom in on one of those decorations. You see that this decoration has its own smaller decorations attached. Here's another area of the Mandelbrot set. You see that this decoration looks a little different from the previous one. Here's another decoration. If I zoom on it, it looks, again, very different from the previous decorations. Here's another one. And finally, if I look in the area between the two largest bulbs, we see a lot of different decorations. Magnify one of them, and that decoration, too, looks very different. So, what is the mathematics behind all of these decorations? What do they mean mathematically? Well, by the end of the hour, I hope that you'll recognize this decoration as being associated with the number 1/3. Here is the 2/5 decoration on the Mandelbrot set. Here is the 1/4 decoration, and the 6/13 bulb, and the 10/21 bulb. As you see, all of these decorations look very different, and they have their own mathematical meaning, which we're about to discuss. Now, where does the Mandelbrot set come from? How does it arise? Well, it arises from the process known as iteration. Now, iteration means to repeat a process over and over again. Now that we have readily available computers, we can repeat these processes over and over again hundreds and thousands of times. In fact, some of the experiments I'll do later will involve over 40 million iterations, all done in a fraction of a minute. Now, what is the process that's repeated to produce the Mandelbrot set? Well, to iterate, to produce the Mandelbrot set, we need to start with a mathematical function. The function that governs the Mandelbrot set is the simple quadratic expression x squared plus a constant. Here c is some constant, and as I go along, I'll have to tell you exactly what that constant is, what c is. We'll also need a place to begin the iteration. That's what we know as the seed. The seed is just some number x0. It may be a real number, it may be a complex number. We'll have to specify exactly what it is. Now, how do we iterate x squared plus a constant? Well, it's easy. We start with the number x0, throw it into the function, that is compute x0 squared plus c. That yields a new number, which we call x1. And now we repeat that process. Throw x1 into the function, compute x1 squared plus c, get a new number x2. Use that as the input for the next iteration. x2 squared plus a constant yields x3. And again, x3 squared plus a constant yields x4. And so you see the process of iteration produces a list of numbers. That list of numbers has a name. It's what we call the orbit of x0. Now, the main question in this area is, can we predict the fate of orbits? Can we tell what's happening to that list of numbers? As you'll see, it's the Mandelbrot set that provides a geometric answer to that question. The Mandelbrot set allows us to answer the question, what is the fate of orbits? Well, just to make sure you're with me, let's go through a couple of simple examples. Let's start with x squared plus 1. So I choose the constant to be 1, and now let me choose the seed to be 0. So I start with x naught is 0, throw 0 into the expression, compute 0 squared plus 1 is 1. Then do it again. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 5 squared plus 1 is 26. 26 squared plus 1 is, you with me? It's big. Big squared plus 1 is, yeah, that's right, bigger. So you see that under iteration of x squared plus 1, the orbit of 0 goes off to infinity. The fate of the orbit of 0 is it tends to infinity. Let's do another example. Let me change the constant now to 0. So I'm going to iterate x squared plus 0. Again, I'll choose the seed 0, and now let's iterate. Start with 0. 0 squared plus 0 is 0. 0 squared plus 0 is 0. Iterate again, of course, get 0. And what you see is the fate of this orbit is much different. When we change the constant down to 0, we see that the orbit of 0 is fixed. It never moves. It's what we call a fixed point. One more example. Let me now change the constant to -1. So I'm going to iterate x squared minus 1. Again, I'll start with the seed 0. So x naught is 0. And now iterate. 0 squared minus 1 is -1. Square that minus 1, you get 0. Iterate again, get -1. Square that minus 1, you're back at 0. So what you see is this orbit tends to oscillate back and forth between 0 and -1. This orbit is, if you will, a 2-cycle. So you see that as we vary the constant c, we get different answers to the question, what is the fate of the orbit of 0? So what I'd like to do now is turn to the computer and use the computer to compute several other examples of orbits under x squared plus c. With this little program, I can iterate the function x squared plus a constant. I need to tell the computer what the constant is. For example, let me choose the constant minus 1.1. So I'm going to iterate x squared minus 1.1. I need the seed. Let me put in the seed again, 0. And now the computer will compute the first 1,000 points on the orbit of 0 under iteration of x squared minus 1.1, and there the orbit is. Notice that we start here at 0, iterate once to get -1.1, again, and observe that eventually, by the time we've iterated 26, 27, 28 times, this orbit begins to cycle back and forth between minus 1.09 and 0.09. So this orbit, too, eventually tends to a 2-cycle. Well, let me display this same 2-cycle in a slightly different way. Let me display the orbit as a time series. In this chart here, I'll plot on the horizontal axis the iteration count, starting 1, 2, 3, 4, etc. And then on the vertical axis, I'll plot the actual numbers that come out of iteration. So again, we'll iterate x squared minus 1.1, starting at the seed 0, and here's what the time series looks like for this orbit. Notice that the numbers oscillate back and forth between just above 0 and just below -1. This orbit is a cycle of period 2. Let's do another example. Let me change the constant now down to -1.3. So I'm going to iterate x squared minus 1.3. Again, I'll start with the seed 0 and display the results of iteration as a time series. Notice the time series now is slightly different. Instead of oscillating with period 2, this cycle cycles with period 4. Notice that at this particular iteration we're very high, then go moderately low, moderately high, very low, and then return back where we were. So this is a cycle of period 4. Another example, let me lower the constant a little bit more, this time down to minus 1.38. So I'm going to iterate x squared minus 1.38. As always, start with the seed 0, display the result as a time series, and now you see something that at first looks like a cycle of period 4, but if you look closely, it's really a little different. Let me stop the iteration right about here. Notice that at this point we're at essentially 0. If I iterate 1, 2, 3, 4 times, I come back close to 0, but actually a little bit below. I've got to iterate 5, 6, 7, 8 times before I return to 0. So this is a cycle of period 8. One last example, let me now lower the constant down to negative 1.99, very close to minus 2. Start with some seed and iterate, and now notice that the time series is quite a bit different. Instead of cycling with some period, this time series seems to go all over the place. This is what mathematicians call chaotic behavior. There is no pattern to the fate of this orbit under iteration of x squared minus 1.99. Let me show you that in a slightly different way. Let me take the same orbit and now display it as a histogram. What I'll do is compute 20,000 points on that orbit and then plot a histogram between minus 2 and plus 2. That is to say, I'll divide up that interval into about 300 bite-sized little intervals. Each time the orbit enters one of those intervals, I'll increment the histogram by 1 unit. So here's the histogram of that orbit. And what you see is that this orbit essentially fills up the entire interval between plus and minus 2. It visits every little subinterval a number of times. So there really is no pattern to this particular orbit. As I said, this is an example of chaotic behavior, one of the more interesting topics in contemporary mathematics. Okay, good. Well, let me now turn back and just make one fundamental observation about what we've seen. This is the fundamental observation that in fact lurks behind the Mandelbrot set. The observation is this: when we compute the orbit of 0, sometimes it goes to infinity. The only other thing that can happen is that the orbit does not go to infinity. So there's a dichotomy. Either the orbit of 0 goes to infinity or it does not. When the orbit does not go to infinity, it could go to a fixed point, it could cycle with period 2 or 4 or whatever, or it could behave chaotically, but basically there are two things that can happen. Either the orbit of 0 goes to infinity or it does not. Okay, well, the natural question is, where does the Mandelbrot set come up in all of this? The Mandelbrot set arises again by iteration of x squared plus a constant, but now both x and c, the constant, are complex numbers. So we'll be doing complex iteration. That occurs exactly as with our previous examples, so let's make sure you're with me by doing a couple of examples. Let's iterate, for example, x squared plus I. So I choose the constant now to be the imaginary number I. As before, we'll start with the seed 0, so x naught is 0. Now, to add some geometry to the process, let me not only compute the numbers, the complex numbers on the orbit, let me also display the orbit geometrically by depicting the points on the orbit in the complex plane. So we start with 0, throw 0 into x squared plus I, we get I. Then I squared plus I is negative 1 plus I, and there's negative 1 plus I in the complex plane. Square negative 1 plus I and add I, turns out you get negative I. So there's the next point on the orbit. Square negative I, add I, you're back at minus 1 plus I. So we've seen that before. Iterate again, get negative I. One more time, get minus 1 plus I, negative I. What you see is this orbit begins to bounce back and forth between negative 1 plus I and minus I. So again, the fate of this orbit is it eventually cycles with period 2. So just as we saw with real iteration, complex iterations may yield cycles or chaotic behavior just as before. The orbits may also go off to infinity. Here's an example of that. Let's iterate now x squared plus 2i. Again, I'll start with the seed 0, so x naught is 0. Now 0 squared plus 2i is 2i. Square that, add 2i, you get negative 4 plus 2i. Square that complex number and add 2i, you can check, you get 12 minus 14i. Square that complex number, add 2i, you get a larger complex number. Iterate again, you get a very large complex number. And what you can check is that this orbit, too, goes off to infinity. So, just as with real iterations, there's a fundamental dichotomy. The main observation is sometimes these orbits go to infinity, and sometimes they do not. Now, that's the observation that lies behind the Mandelbrot set. For the Mandelbrot set is nothing but all the c values in x squared plus c for which the corresponding orbit of 0 does not go to infinity. Let me say that again. The Mandelbrot set is a picture of the c values in x squared plus c, having the property that if you compute the orbit of 0 for x squared plus that c, that orbit does not go to infinity. It may go to a fixed point, it may cycle, it may behave chaotically, but it does not go to infinity. So let's look at the Mandelbrot set. Here is the Mandelbrot set. To orient you in the complex plane, remember the Mandelbrot set is a picture of the complex c values. Let me put a grid on the complex plane. Here are the real and imaginary axes in the complex plane. The point I is more or less right here. Negative I is down below. And on the real axis, we run from -2 out to approximately 1. So there are the complex numbers. There is the Mandelbrot set in the complex plane. Just to orient you in the plane, the black points are the points that lie in the Mandelbrot set. So each point that I've colored black here is a complex c value which lies in the Mandelbrot set. So that means that the corresponding orbit of 0 does not escape. On the other hand, the points that I've colored with various shades are those that do not lie in the Mandelbrot set. So those are the c values for which the orbit of 0 escape. Now, what the colors mean here is essentially how quickly the orbit of 0 escapes to infinity. I color a point shades of red or orange if the corresponding orbit of 0 tends to infinity fairly quickly, 5, 10 iterations. I color a point shades of yellow or green if the orbit tends to infinity more slowly, after maybe 20 or 30 iterations. On the other hand, I color the point shades of blue or violet if the orbit takes a relatively large number of iterations before you start saying big, bigger, and so forth. So I color a point blue if it takes maybe 40 or 50 iterations to escape to infinity. Okay, well, now let me turn to the computer and use it to investigate the Mandelbrot set in more detail. With this little program, I'll be able to plot the fate of the orbit of 0. What I'll do is put the cursor down on or around the Mandelbrot set, and then view in the upper left-hand corner the fate of the orbit of 0. So let me choose a c value right here in the middle of the largest black region. And then as I move c around, notice what happens up in the screen in the upper left-hand corner. What you see is basically one point. That point sometimes is circled. That's because what I'm doing in this program is actually computing 50 points on the orbit of 0 and circling the last one. So we see here that all of these points are bunched very close together. So the conclusion is for the c values inside this large black region, the fate of the orbit of 0 is it tends to just one complex number. It tends to a fixed point. Now, if I move the cursor outside of the Mandelbrot set, suddenly something very different happens. Suddenly the orbit of 0 goes off to infinity. Come back into the Mandelbrot set, and we're attracted to just one point. leave the Mandelbrot set, and the orbit explodes off to infinity. Come back in, we tend to one fixed point. Of course, that's the very definition of the Mandelbrot set. The Mandelbrot set is precisely those c values for which the orbit of 0 does not go to infinity. Now, if the only case were the orbit of 0 goes to infinity or the orbit of 0 goes to a fixed point, there wouldn't be much to the Mandelbrot set. In fact, that's the meaning of all these other decorations. Watch what happens when I move the cursor into the second bulb on the left of the main piece of the Mandelbrot set. Notice that as I move C around, the orbit of 0 tends to 2 points. One of those points is circle. That's just the last of the 50 iterations I'm taking here. So what we conclude is for C inside this region, the orbit of 0 tends to cycle with period 2. If I move the cursor into the next region, we see that the orbit of 0 cycles with period 4. If I leave the Mandelbrot set, the orbit of 0 goes off to infinity. When I come back in, we tend to a cycle of some period. Leave the Mandelbrot set, we explode off to infinity. Come back into the Mandelbrot set, we tend to a cycle of some period. That, in fact, as I said, is the meaning of all these little decorations. For example, on the northern part of the Mandelbrot set, if I put the cursor in there, we see that the orbit of 0 tends to cycle with period 3. If I go down to the symmetrically located bulb in the southern part of the Mandelbrot set, again, we see that the orbit cycles with period 3. Up here in the northeast is a bulb in which the orbit cycles with period 4. Again, the circled orbit simply means the last point on the orbit that we reach after 50 iterations. Over on the northwest side is another decoration. That decoration has period 5. Next to it is a smaller decoration. Let me put the cursor in there. When I do, if you count carefully, you'll see that there are in fact 7 points. So the orbit of 0 for C in this bulb tends to cycle with period 7. This is a period 7 bulb. As I move the cursor around the Mandelbrot set, there's all sorts of different periods. The Mandelbrot set is replete with these different bulbs with differing periods. Okay, but if I leave the Mandelbrot set, the orbit of 0 tends off to infinity. When I come back, the orbit of 0 tends to a cycle of some period. So, now that we understand the periods of the bulbs, let me show you how a mathematician goes about analyzing the structure of the Mandelbrot set. Here is the Mandelbrot set. As we know, a C value in this large black region corresponds to the orbit of 0 going to a fixed point. Right to the left of it is another black region where the orbit of 0 tends to a cycle of period 2. Let me magnify that region. As you see, it looks like a big black circle. Now, just to the left of that is another region. We just saw that the orbit of 0 for C in this region tends to a cycle of period 4. Let me magnify it. Again, it looks like a big black circular region. As it turns out, just to the left of this region is another region, and in this region the orbit of 0 tends to cycle with period 8. Here's a magnification of that region. Sort of looks exactly the same. But it's not exactly the same. Look at the antennas on the period 8 bulb as opposed to the previous decoration. That was the period 4 bulb, and the previous decoration to that, the period 2 bulb. Notice these antennas here are relatively short for the period 2 bulb, but for the period 4, they're significantly longer. For the period 8 bulb, they're longer still. So there's something in the antennas attached to these bulbs that tells me that this is period 8, whereas that is period 4. So let me show you that in another way. Here's period 8. Let me magnify this little region right down here. When I magnify that little region, we see a small copy of the Mandelbrot set. So buried deep within the Mandelbrot set are small copies of exactly the Mandelbrot set. But if you look at the antennas attached to this baby Mandelbrot set, you see that they're much different from the original. By looking at these antennas, I can tell you exactly what the period of the orbit of 0 would be if I placed the cursor right down here. Let me show you how to do that. Here again is the Mandelbrot set, and at the top we saw that if we chose a C in this decoration, the orbit of 0 would eventually cycle with period 3. This is the period 3 bulb. Let me magnify it. When I do, you see that the period 3 bulb has an antenna which has a junction point from which 1, 2, 3 spokes emanate. Another example, over here on the northeast side of the Mandelbrot set was a decoration. We saw earlier that that was the period 4 decoration. When I magnify it, you see that the antenna has a junction point from which now 4 spokes emanate. One more example, over here on the northwest side of the Mandelbrot set, we saw a period 5 bulb. When I magnify it, again, you see that the junction point has exactly 5 spokes leading away from it. So you can read off the period of the bulb by looking at the antenna. Here's another example. Way down inside here in the Mandelbrot set is another decoration. What's the period of this decoration? That is, what would happen to the orbit of 0 if I chose a C value inside here? Well, that orbit of 0 would be attracted to a cycle of period 7 because there are 7 spokes on this antenna. Okay, don't forget to count this one here. Another example, what's the period of this bulb? Well, let me help you out. Let me magnify the junction point. When I do, if you count these spokes and remember where you started, you see that there are exactly 13 spokes coming out of this junction point. So this decoration is the period 13 bulb on the Mandelbrot set. Well, there's actually much more going on in this Mandelbrot set. Let me go back to this decoration. Let me magnify it. You recognize this now as the period 3 bulb. There are lots of little black blips here. Here's one of them. Let me magnify it. When I do, you see another copy of the Mandelbrot set, but notice the antennas on this small Mandelbrot set. Notice that all of the antennas have junction points from which 3 spokes emanate. Junction points from which 3 spokes emanate. So that tells me that this is one of the baby Mandelbrot sets hanging off the period 3 bulb. Here's another example. This is a period 4 bulb, little black blip here. Magnify it. Again, you see an interesting antenna structure. There in actuality is a long, thin strip of black that runs through these antennas here. Can't really see the black because of the resolution of the screen, but what you do notice that everywhere you look, you see junction points from which 4 spokes emanate, indicating that this is one of the baby Mandelbrot sets hanging on the period 4 bulb. Here's the period 5 bulb, little black blip. It too is a Mandelbrot set. Notice that the antenna structure is characteristic. This antenna structure always has junction points with 5 spokes emanating. One more example. That's the period 13 bulb, little black blip. If you look closely at any of these junction points, you'll see that there are exactly 13 spokes emanating from that junction point. Okay, now we've only been dealing with decorations that hang off the main black cardioid-like region in the Mandelbrot set. We could also look at the decorations that hang off any of the other decorations. For example, let me look at the region between period 1 and period 2. Here was the decoration of period 13 that I examined a moment ago. If we look at the decorations hanging off the period 2 bulb, you see that they're very different in appearance. That, in fact, is true. Every decoration hanging off a subdecoration has its own individual characteristic. Let me magnify this region here. Here you see that the decorations are indeed quite a bit different. By counting the number of spokes on this antenna, and by noticing that this antenna actually spirals into a particular point and then spirals away again in another branch, I know that this decoration is the period 13 times 2 decoration, so the period 26 decoration hanging off the period 2 bulb. Let me show you this little junction point right here. Very complicated structure. The moral of the story is, though, that you can walk up to an expert on the Mandelbrot set on the street, show him or her just the smallest piece of the boundary of the Mandelbrot set. That person will just say, oh, that's nothing but the period 78 bulb hanging off the period 13 Mandelbrot set, which is attached to the period 5 decoration on the northwest side of the Mandelbrot set. In fact, every area of the Mandelbrot set has its own identification, and by looking at the geometry of the Mandelbrot set, you can read off exactly what that period, what those dynamics are. In conclusion, we see that the Mandelbrot set possesses a tremendous amount of intricate geometric structure, but that using a little bit of dynamics, we can understand exactly what that structure means. In the next segment of this video, we'll delve even more deeply into this geometry, see that the Mandelbrot set possesses a wealth of information about not just the orbit of 0, but in fact the orbit of any other seed. In this segment, we're going to delve more deeply into the geometry of the Mandelbrot set. As we saw in the previous segment, the Mandelbrot set comes equipped with lots of tiny decorations, each of which has its own mathematical meaning. In this segment, we'll try to understand how all of these decorations are arranged around the boundary of the Mandelbrot set. Now, to do that, we have to introduce one new notion. That's the notion of a Julia set. Once we do that, I'll be able to, as promised, show you how to count and how to add. Well, let's begin by recalling what we saw in the last segment. The Mandelbrot set has all of these tiny decorations arranged around it. We saw that each has its own period. For example, this bulb has period 3. Over here we saw period 4. On the northwest side was period 5. Lots of other decorations. There was period 7, period 2, period 4. Down below was period 3. In fact, there are thousands and thousands of these small decorations. Way up at the top is a period 77 decoration. And over here is a period 231 decoration. And as we'll see, there are decorations of virtually every period. Now, the question we want to discuss now is how are all of these bulbs arranged around the boundary of the Mandelbrot set? As I said, to understand that, we have to introduce the notion of a filled Julia set. The Julia sets actually go back to the work of Gaston Julia, a French mathematician who studied these objects back around 1918 or 1920. It's amazing to read Gaston Julia's old papers and see that he understood exactly how complicated these incredibly rich Julia sets are. Okay, to understand a Julia set, we're also going to iterate. That means we've got to start with x squared plus c, but now, unlike the Mandelbrot set, I'll fix that c value. Okay, I'll again iterate x squared plus that c value, but now not only for the orbit of 0, but rather for all seeds. So instead of just considering the orbit of 0, we'll consider the orbit of 1, of I, of 1 plus I, of all possible complex numbers. Now, what's the Julia set? The filled Julia set is simply all those seeds whose orbit under x squared plus that given c does not escape to infinity. Okay, let me say that again. The filled Julia set consists of all the seeds whose orbits remain bounded under iteration of x squared plus the constant. Okay, as an example, let's compute the filled Julia set of x squared plus the constant 0. Okay, or the filled Julia set of just x squared. To do that, we've got to sample all the possible seeds, all the possible complex numbers that can serve as seeds, and see what's the fate of their orbits under iteration. So let's ask, for example, is the seed 0 in the filled Julia set for x squared? Well, 0 squared is 0, 0 squared is 0, 0 squared is 0. That seed obviously does not have orbit that escapes. That orbit stays fixed, so 0 is in the filled Julia set. Another example, how about x naught equals 1? Well, the orbit of 1 is also fixed. 1 squared is 1. 1 squared is 1. The orbit of 1 stays bounded. It does not escape. So yes, 1 is in the Phil-Julius set. Another example, I squared is -1. Square that, get 1. Square that, get 1. And again, you see that this orbit stays bounded. It does not escape. So I is in the Phil-Julius set. What about 2i? Well, if we start with 2i and square it, we get -4. Square that, get 16. Square that, get 256. 256 squared is big. And the orbit clearly goes off to infinity. So this orbit is not in the Phil-Julius set. This orbit escapes. And to compute the orbit, the Phil-Julius set rather of x squared, we'd have to do this procedure for all possible complex number, for all possible seeds. Well, if you do this experiment, what you'll find is the set of seeds whose orbits do not escape to infinity are all those complex numbers on or inside the unit circle in the plane. That is the unit disk in the complex plane. So here's a picture of the Phil-Julius set for x squared. This is the circle of radius 1 centered at the origin. As we saw, 1 and 0 and I are in the Phil-Julius set, but 2i is not. So we color the Phil-Julius sets exactly as before. Black means the complex seed is in the Phil-Julius set. Colors mean the complex seed is not in the Phil-Julius set. Well, it's important to realize the subtle difference between the Mandelbrot set and these Phil-Julius sets. For the Mandelbrot set, we let C vary. We let the complex constant C vary. In each case, we computed the fate of the orbit of 0. For the Phil-Julius sets, we do something very different. In this case, we fix the C value and compute the fate of all possible seeds. So for the Mandelbrot set, we look at just the orbit of 0. For the Julius set, we look at the set of all possible orbits. Well, what I'd like to do now is turn to the computer and ask the computer to compute a variety of these filled Julius sets. What we'll see is they assume all kinds of incredibly complicated fractal shapes. So, in order to compute the filled Julius sets, we need to fix a C value. We need to choose a C value. What more natural way to choose a C value than to pick it from the Mandelbrot set? So what I'll do is use the cursor to choose a C value in or around the Mandelbrot set, and then compute the corresponding filled Julius set. For example, if I choose a C value right here, under the cursor, over here you see that I've chosen the C value minus 1.01 plus 0.009i, so I've chosen a C value near -1. Let me now compute the filled Julius set for this C value. What the computer is doing is actually computing the fate of 300 by 300 orbits in the complex plane, and displaying them either in color or in black, depending on whether the orbit is not in the filled Julius set or the seed is in the filled Julius set. And here you see that the filled Julius set for this particular C value is a fairly complicated shape. Let me show you that by magnifying a certain portion of this picture. Let me magnify the region right here. You apparently see is a disk on top of another disk. When I magnify that, you see that there's much more to the story. The computer is now coming by and refining the image. As it does, you see that this filled Julius set consists of lots of tiny disks atop even larger disks. Hey, let me not fully bake this picture. Rather, let me come back and magnify another portion of this image. Let me magnify this portion. When I do, you see virtually the same image. As the computer comes by and refines this image, that is, computes the filled Julius set in more detail, you see essentially the same structure. That is to say, as we zoom in on this Phil-Julius set, we seem to see the same image over and over again. That's what's known as self-similarity. It's one of the hallmarks of these Phil-Julius sets. They're fractal images. They're often self-similar. Now, let me show you the previous image. Here it is, looks almost the same. And where it came from, the Phil-Julius set of x squared, essentially minus 1. Okay, let's do another example. Let me choose another C value from the Mandelbrot set. Let me choose a C value up here in the period 3 bulb. Let me choose a C value right about here. I've actually chosen the C value minus 0.128 plus 0.765i. So let's compute the Phil-Julius set for this C value. When I do, you again get a large black region. As the computer comes by and computes more of these orbits, you see that this large black Phil-Julius set resembles a fractal rabbit. You look closely, this rabbit has a main body. Here it is. And as all good rabbits, it has 2 ears attached. But this is a fractal rabbit, so everywhere you look, you see additional pairs of ears. Let me show you that by magnifying a small piece of this filled Julius set. When I magnify this region here, you see that there are ears on top of ears on top of ears, and everywhere you look in this filled Julius set, you see the same sort of structure, the same sort of self-similar structure. This, in fact, is almost always the case. The filled Julius sets for x squared plus a constant are essentially always these intricate images known as fractals. Well, here's a magnification of the ears of the fractal rabbit. Here's where that picture came from, the fractal rabbit itself. Now, in the last 2 images, you've noticed that the filled Julius sets corresponding to C values in the Mandelbrot set are large, albeit complicated, black regions. Watch what happens when I choose a C value that's not in the Mandelbrot set. Let me choose a C value right about here. Okay, so I've chosen a C value just outside the Mandelbrot set. Now let's compute its filled Julius set, and what you see is something completely different. That large black region all but disappears. The filled Julius set shatters. It looks like there's no black in this picture, but if you look at the shading from red to orange to yellow to green to blue, your eye is guided down to what appears to be a series of tiny black dots. In fact, that is the case. The Julius set here is shattered into infinitely many pieces, infinitely many points, what mathematicians call a Cantor set. Another example of that, let's go back and choose a C value outside the Mandelbrot set. Let's choose a C value near the period 3 bulb, say right about here. So I've chosen that C value. Now compute its filled Julius set. And again, you see the filled Julius set virtually shatters. There appears to be no black in this picture, but in actuality there is. There's an infinite number of points that lie in the filled Julius set. In any event, what we see is a rather striking dichotomy. When we choose a C value in the Mandelbrot set, we appear to get one big black region for the filled Julius set. But when we choose a C value outside of the Mandelbrot set, that filled Julius set disintegrates into infinitely many pieces. Well, at this stage, what I'd like to do is turn to a video and show you this dichotomy in much more detail. What we'll do in this video is take a short tour around the Mandelbrot set, weaving our way in and outside of the Mandelbrot set, and then I'll come back and show you what the corresponding filled Julius sets look like. Here's the path we'll take. We start outside the Mandelbrot set, then come in, and then leave the Mandelbrot set, return through the period 3 bulb and exit again, return through the period 4 bulb and exit again. And finally, enter once again into the Mandelbrot set and then out through the period 3 bulb. Now we'll look at the corresponding filled Julia sets for those C values. We start outside the Mandelbrot set in the Cantor set regime, and suddenly, there we go, enter the Mandelbrot set. Julia set becomes a big black region. Now suddenly we'll leave the Mandelbrot set, and again, you see the filled Julia set shatter into infinitely many pieces, which reassemble into a big black region as we come through the period 3 bulb, but then back to a Cantor set as we exit the Mandelbrot set. Here we enter the period 4 bulb and leave the Mandelbrot set. Again, we enter the Mandelbrot set, big black region. Now leave through the period 3 bulb. Here's the fractal rabbit, which then shatters into a Cantor set. So the Mandelbrot set really is an amazing object. It's basically a record of the fate of the orbit of 0 under iteration of x squared plus c, but it also knows the fate of all other orbits, or rather the shape of the set of points whose orbits fail to escape under iteration of x squared plus c. So there's something special about the orbit of 0, something almost magical about the orbit of 0. For this reason, mathematicians call this orbit the critical orbit. Okay, well, now what I'd like to do is return to the Mandelbrot set and use these Julia sets to determine the arrangement of the bulbs around the boundary of the Mandelbrot set. What I'd like to do is assign a fraction to each of these bulbs. Recall that we've already assigned a whole number to each of these bulbs. For example, we called this the period 3 bulb, and this period 5 bulb, and over here a period 2 bulb. What I'd like to do now is assign a fraction to each bulb. The denominator of this fraction will be the period of these bulbs. So for example, this will be the something over 3 bulb, and I've got to tell you what the numerator of that fraction is. Well, it turns out there are 3 ways of determining the numerator. Here's one of them. Let's look at this bulb. Notice, since this is a period 3 bulb, we have a junction point from which 3 spokes emanate. Let me take a trip out the main spoke of this bulb. When I get to the junction point, I'll ask, where is the smallest antenna attached to this junction point? Well, it's pretty clear that the smallest antenna is right over here. We get to that smallest piece of antenna by taking a 1/3 turn in the counterclockwise direction. 1/3 turn from the main spoke. So for this reason, this is the 1/3 bulb attached to the Mandelbrot set. Now I should say at this point that this method of determining the numerator does not always work. In general, you need what we call hyperbolic eyeglasses to determine which is the smallest spoke. The best way to determine the numerator of these fractions is as follows. What we'll do is choose a C value in the middle of this bulb somewhere, say right here, and then display both the Julia set for that C value and the corresponding cycle of period 3. So here it is. Here's the Julia set for that C value. Notice it's our old friend, the fractal rabbit. I'm also showing you the iteration corresponding to this cycle of period 3. And notice what happens as we iterate. This cycle of period 3 tends to jump around, making, roughly speaking, 1/3 of a turn in the counterclockwise direction each time we iterate. So for that reason, this bulb is also called the 1/3 bulb. Finally, look at the shape of this Julia set. It's our fractal rabbit. Here's the main body. There are 2 ears attached. Which ear is the smallest? Well, it's clearly this ear, and notice that we get to it by taking 1/3 of a turn in the counterclockwise direction from the main body. So, for all 3 of these reasons, this was the 1/3 bulb in the Mandelbrot set. Let's do a couple more. Here's another bulb. Let me magnify it. When I do, you notice that there are 4 spokes attached to this antenna. to this decoration rather. So this is the something over 4 decoration. What's the numerator? Well, again, let's move out the main spoke and ask where is the smallest antenna attached to this junction point. Well, you see, it's kind of hard to tell which is the smallest antenna here. It's definitely not this piece. Is it this piece here or that piece? Well, that's why this method doesn't always work. In actuality, it's this piece here, and we get to it by taking a 1/4 turn, 1/4 of a turn in the counterclockwise direction. So this is the 1/4 bulb in the Mandelbrot set. Let's see that in another way. Let's find the Julia set for this C value. There it is. Again, I've also displayed the now period 4 cycle to which the orbit of 0 is attracted. And notice that this period 4 cycle jumps around the Julia set, making a 1/4 turn each time we iterate. 1/4 turn in the counterclockwise direction. Also, look at the Julia set. Again, it's a fractal rabbit, or I should say a degenerate fractal rabbit, because it has a main body, but now everywhere you see are attached 3 rather than 2 ears. Where is the smallest ear attached to this main body? Well, pretty clearly it's right here. We get to that by taking a 1/4 turn in the counterclockwise direction. So again, for all 3 of these reasons, this is the 1/4 bulb attached to the Mandelbrot set. Let's do a couple more. Here's another decoration in the Mandelbrot set. If I magnify it, you see that there are 5 spokes attached to the junction point. So this is the something over 5 decoration. What's the numerator? Well, again, if we go out the main spoke and look for the smallest spoke attached, we've now got to jump not 1/5 of a turn, but rather 2/5 of a turn to get to it. 2/5 of a turn in the counterclockwise direction. So this is the 2/5 bulb. Let's check it with the Julia set. Again, you notice that the cycle now hops around the Julia set, taking a 2/5 jump in the counterclockwise direction at each iteration. If you also look at the shape of the Julia set, here's the main body. Where is the smallest ear attached to the main body? Well, again, it's gotten by jumping not 1/5, but 2/5 of a turn in the counterclockwise direction. So this is the 2/5 bulb attached to the Mandelbrot set. Here's another one. What's the fraction attached to this decoration? Well, again, you count the number of spokes. Don't forget to count the main spoke. There are 7 of them. So this is the something over 7 bulb. Where is the smallest spoke? Well, the smallest spoke is located 1, 2, 3/7 of a turn. So this is the 3/7 bulb. Let's look at the Julia set. There it is. Notice that the cycle now jumps 3/7 of a turn at each iteration. And if you look for the smallest ear attached to the main body, that smallest ear is located 1, 2, 3/7 of a turn in the counterclockwise direction. Okay, I want to gather some more data, so let me do a couple more here. What is the fraction associated with this bulb? Well, as you know, that's the period 2 bulb, so the denominator is 2. What's the numerator? Well, it's kind of hard to see a rabbit here. It's a 1-eared rabbit. Notice that the orbit of 0 jumps back and forth, essentially 1/2 of a turn at each stage. So this is the 1/2 bulb attached to the Mandelbrot set. It's the 1/2 bulb here in Boston. In other areas, it may be the 1/2 bulb. Anyway, a couple more. What's the fraction associated to this bulb? Denominator is 5. And the numerator should be jump 1, 2, 3/5 of a turn. So this is the 3/5 bulb, and check it with the Julia set. Again, note that the orbit jumps 3/5 of a turn each time, and the smallest ear attached to this rabbit is located 3/5 of a turn in a counterclockwise direction. Well, at this stage, we've gathered a lot of data about the fractions associated to these bulbs or decorations. What I'd like to do now is turn back to the computer and try to put all of this data together and see if we can understand the arrangement of these fractions. As we saw, this was the 1/4 bulb. Up above was the 1/3 bulb. Here was 2/5. Over here, 3/7. Here was the 1/2 bulb. And over here is the 3/5 bulb, the 2/3 bulb, and the 3/4 bulb. You see something about the order of these fractions? Notice that they're in exactly the right order. 1/4 is smaller than 1/3, which is smaller than 2/5, smaller than 3/7, and so on. These bulbs are arranged in the exact order of the fractions of the rational numbers. Moreover, if you give me any fraction whatsoever, there's a bulb that corresponds to that fraction. If you give me any fraction in lowest term, no matter what the numerator or denominator is, I can find a bulb that corresponds to that fraction, and moreover, the geometry of that bulb is exactly as we saw before, the number of spokes, the orbit of 0, etc. For example, if you give me the fraction 109 over 333, well, that's a number that's just less than 1/3, and we've seen that that's the 1/3 bulb. So attached to the Mandelbrot set has to be a tiny decoration corresponding to exactly that number. That is to say, there must be 333 spokes on the antenna, and if you look at the orbit of 0, that orbit of 0 must jump by 109 ears each time you iterate. If you give me another fraction, for example 1/500, then there must also be a bulb that corresponds to that number. That is to say, if we magnified this, this decoration right here, you'd see exactly 500 spokes on the antenna, and the corresponding orbit of 0 would jump by 1/500th of a turn at each stage. Well, at this stage, what I'd like to do is show you a video of all of this. I'd like to show you a video that takes you on a tour around the boundary of the Mandelbrot set. What we're really doing, though, is going through all of the rational numbers. As you look at the video, you'll see the corresponding Julia sets for each fraction. If we slowed the video down, you could read out exactly what number you're at. This is the reason why I like to think of the Mandelbrot set as a real number line. Okay, only the Mandelbrot set is a little bit different from the ordinary real number line. You look at the real number line, in general can't tell what the number 1/3 is or what the number 4/7 is. They all look the same. But if you use the Mandelbrot set as a real number line, then by looking at the configuration of these antennas, you can tell exactly what number you're at. The Mandelbrot set is really a gorgeous real number line. So now let's turn to the video. What we'll do in this video is actually run around the boundary of the Mandelbrot set. Actually, we'll be just outside the boundary of the Mandelbrot set, so sometimes we'll see Cantor sets for the filled Julia sets. Other times we'll see the big black blobs corresponding to the filled Julia sets when we're inside the Mandelbrot set. So let's look at the video. Here's the path we'll take in the Mandelbrot set. We're running around the boundary, actually just outside the boundary of the Mandelbrot set. So as I said, sometimes in the bulbs, other times we're outside. Here's where we begin. We're now outside the Mandelbrot sets. And now we're going to start passing through the bulbs. Each flash of black is a filled Julia set. And if we stopped the film at any stage and you counted the ears attached to the main body, you'd be able to read off exactly which fraction you were at. For example, we're now passing through the 1/6 bulb. If you count here, you'll see that we're in the 1/5 bulb. Now we're passing through the 1/4 bulb. If you watch quickly, you'll see the fractal rabbit corresponding to the 1/3 bulb. There it is. And then on through all of these rational numbers until we end up at the 1/2 bulb. So now you know how to count. Now let's figure out how to add. Let's see how to use the Mandelbrot set to add fractions. This is fun. Okay, we saw that this was the 1/3 bulb, and down here was the 1/2 bulb. And now the largest bulb in between the 1/3 and 1/2 bulb is right here. Remember, this was the 2/5 bulb. Okay, so the largest bulb between 1/3 and 1/2 is 2/5. Let's do this again. Here I've magnified a portion of the Mandelbrot set. Over here we recognize the 1/2 bulb. Up here, if you look closely, you'll see the 2/5 bulb. And now in between the largest bulb is this one here. And that's the 3/7 bulb. So do you see how to obtain the largest bulb in between two given bulbs? What you do is you take the fractions and add them just the way you always wanted to add fractions. Namely, add the numerators and add the denominators. To obtain the largest bulb between two given bulbs, you add the numerators and add the denominators. It's amazing that this works. Now, I don't recommend you doing this kind of addition in any of your mathematics classes. Please don't say that this is the way Professor Devaney taught you to add fractions. In fact, this kind of addition is a very famous type of operation in mathematics called Fourier addition. In higher mathematics, you often encounter this in what's known as number theory, when, roughly speaking, you'd like to obtain the fraction between two given fractions whose denominator is the smallest. You do what we just did. You add the fractions by adding the numerators and adding the denominators. Let's do one last example. Here is the 1/3 bulb. Down here, you recognize our friend, the 2/5 bulb. What's the largest decoration in between? Well, it's clearly right here. What's the fraction associated to this bulb? Well, just as before, we add the numerators and add the denominators, and we see that the new decoration, the largest decoration, is the 3/8 bulb, because 1/3, quote unquote, plus 2/5 is 3/8. And if you look at the decoration here, you see that there are precisely 8 spokes attached to this decoration, and the smallest is right here, 3/8 of a turn. Well, there are lots of other amazing things that happen in the Mandelbrot set. Do you remember the Fibonacci sequence? You want to see the Fibonacci sequence in the Mandelbrot set? Well, remember what the Fibonacci sequence is. We start with 1 and 1. Then the next number is add 1 and 1, get 2. Then add 1 and 2 and get 3. 2 and 3 gives 5. 5 and 3 gives 8. That's the famous Fibonacci sequence. Let's see that in the Mandelbrot set. This, of course, is the period 1 bulb. Let's call the entryway to the period 1 bulb 1. Now, I'm not going to talk about these fractions anymore. I'm just going to use the periods of the bulbs, so the denominator of these fractions. Over here is the period 2 bulb. What's the largest bulb between 2 and 1? Well, if we go on the top part of the Mandelbrot set, we know we add those two numbers to give us the period 3 bulb. What's the largest bulb between 2 and 3? Well, it's period 5. And largest between 5 and 3 we just saw was period 8. And the largest between 8 and 5 was 13. The largest between 13 and 8 is 21, and so forth. And you see the well-known Fibonacci sequence converging down to a point in the Mandelbrot set. There's an incredible array of different mathematics going on in the Mandelbrot set. There's another sequence I'm very fond of. Okay, look at this sequence. Again, we call this period 1, and over here is period 2. As we've just seen, the largest bulb between period 1 and period 2 is the period 3 bulb. And the largest bulb between period 3 and period 1 is the period 4 bulb. And the largest between 1 and 4 is 5. And the largest between 1 and 5 is 6, and so forth. The next is 7. This is, I think, is a very famous sequence that I'm sure you'll see many times in the future, 2, 3, 4, 5, 6, 7, etc. I've always wanted to have something named after myself, so I call this the Devaney sequence, and I hope that whenever you encounter this in the future, you'll call it by its proper name, the Devaney sequence. So, all joking aside, I hope you've come to appreciate the mathematics that lurks behind the Mandelbrot set. As you recall, the Mandelbrot set was first seen in 1980. And much of the mathematics we've talked about here today is mathematics that's been developed during your lifetime. But there's so much more to be done in this area. We still don't completely understand the Mandelbrot set. For example, we've talked at length about the bulbs corresponding to the rational numbers, to the fractions. There are also irrational numbers around the boundary of the Mandelbrot set. What happens there? Well, we don't have bulbs or decorations corresponding to these irrational numbers. Still, there's a tremendous amount of fascinating dynamics that goes on. In fact, in 1994, the French mathematician Jean-Christophe Yocoz received the Fields Medal, the mathematician's equivalent of the Nobel Prize, for work in exactly this area, trying to understand what happens at these irrational bulbs. And then we've only been discussing x squared plus a constant. What happens when we iterate other mathematical functions, for example, cubics, or trigonometric functions, or exponential functions? There the situation is much more difficult. We have very little idea of what happens when we iterate things like cubic polynomials. Finally, you might ask, what about the applications of all of this mathematics? Well, to be honest, since this mathematics is so new, and since it really is still in the developmental stage, the real applications have yet to come. Yet there are many scientists in all disciplines using these kinds of ideas to attack important problems. For example, many ecologists are using these kinds of iterative models to study the growths of populations. Similarly, physicians are using these ideas to study such diverse topics as cardiac arrhythmia, the growth of tumors. Meteorologists use these ideas all the time to help in weather prediction. Economists use this to study global markets, the Dow Jones average, et cetera, et cetera. Finally, no matter what the future holds for this kind of mathematics, I hope you'll agree that this mathematics is at once exciting and accessible and beautiful.